Have you ever stopped and wondered how scientists study things they just can't control? Like us. Today, we're going to step out of that perfect, sterile lab and right into the messy, unpredictable real world to find out how research actually gets done. So think about it. Let's say you want to know if a new teaching method helps students learn better. You can't just randomly assign kids to different schools, right? Or what if you're trying to understand the long-term effects of a health condition? You can't ethically give someone that condition. So when that gold standard, the controlled experiment, is totally off the table, how do we find solid answers to some of the most important questions out there? In a perfect world, yeah, every study would be a controlled experiment. You'd have people randomly assigned to either a treatment group or a control group. That's the gold standard because it's hands down the best way to prove cause and effect. But as we all know, life is messy. It just doesn't fit neatly into a lab. And that means scientists need a whole different set of tools to figure out the complexities of the real world. And that's exactly where we're going today. Welcome to the Researcher's Toolkit for the Real World. When that perfect experiment just isn't an option, two really powerful strategies come into play: non-experimental and quasi-experimental designs. Let's break down what those are and why they are so important. Okay, so the biggest difference between these two approaches really boils down to just one word: control. A non-experimental design, well, it pretty much just observes the world as it is. It makes little to no attempt to control for things that could mess up the results. A quasi-experimental design, on the other hand, tries its best to mimic a true experiment. It's actively working to minimize those threats to our confidence. Now, I just mentioned threats, and that brings us to a super important idea: internal validity. Put simply, it's all about confidence. How sure can we really be that our intervention, our treatment, actually caused the change we're seeing? Any other possible explanation, what scientists call a confounding variable, is a threat to that confidence. So the whole goal of a good research design is to stamp out as many of those alternative explanations as possible. All right, let's dive into a really common problem. What do you do when you have to study groups that already exist? I'm talking about comparing two different classrooms or two departments at a company or even two neighborhoods. How can we learn from them when we can't control who's in which group? This is where something called the non-equivalent group design comes into play. And this really gets to the heart of the challenge. Because the groups are already formed, researchers can't use that gold standard of randomly assigning people. And that's a big deal because it means the groups might be different from each other in really important ways from the very beginning, which could totally throw off the results. So, how do we get around this? How can we add a layer of control? Well, here's a pretty clever fix. You can upgrade to a quasi-experimental design using what's called a pre-test, post-test structure. It's a really powerful three-step process. First, you measure both groups to get a baseline to see where they stand before you do anything. Then, you introduce your treatment, like that new teaching method we talked about, to just one of the groups. And finally, you measure both groups again. This lets you see if the treatment group changed more than the control group, which gives you much, much stronger confidence that your intervention was actually the cause. Okay, so we've tackled pre-existing groups, but what about a challenge that's even bigger, even more fundamental? I'm talking about time itself. How on earth do scientists study the way we change and grow over months, years, or even across an entire lifetime? For this massive challenge, researchers turn to a special set of tools called developmental research designs. And just like the name says, their whole purpose is to look at changes in behavior that are related to getting older. And there are two main ways they go about this. The two big approaches are probably best understood with a simple analogy. Think of a cross-sectional design as taking a quick snapshot. You measure different groups of people, say a group of 20-year-olds, a group of 40-year-olds, and a group of 60-year-olds, all at the exact same time. A longitudinal design, on the other hand, is like watching a movie. You take one group of people and you follow them for years and years, measuring them again and again as they age. Now, the huge advantage of that cross-sectional snapshot is, you guessed it, speed. You can compare 20-year-olds to 80-year-olds today without waiting 60 years. But, and this is a big but, here's the catch. Are the differences you're seeing really because of age, or is it because these groups grew up in completely different generations with different technology, different education, different world events? That's what's called a cohort effect, and it's a huge potential pitfall for this kind of study. So that longitudinal movie design, it totally solves the cohort problem. Since you're following the exact same group of people, there are no cohort effects. But, of course, it has its own massive headaches. For one, these studies are incredibly time-consuming and expensive. And a really big one, people tend to drop out over time, what researchers call attrition, which can seriously mess up the results. I mean, can you imagine trying to keep track of the same group of people for decades? It is not easy. So as you can probably see, there is no single perfect method that just works for every single situation. Each approach we've talked about comes with its own unique set of pros and cons. The real skill for a researcher isn't just knowing what these methods are, it's knowing when to use which one. So here's the big takeaway from all this. Research design is a balancing act. It's all about trade-offs. You're constantly trading control for practicality, and you're trading speed for accuracy. That quasi-experimental design gives you more confidence, but it might be way harder to pull off. A cross-sectional study is fast, but a longitudinal one is more accurate if you want to see how people truly change. The genius of good science lies in picking the right tool for the job. So let me leave you with a final thought to chew on. Imagine you're a researcher, and your job is to figure out if a new city park actually improves the well-being of the people who live nearby. You can't randomly assign people to live near the park. So, looking back at our toolkit, which design would you pick, and more importantly, what trade-offs would you be making? It's a really fascinating puzzle, and now you've got the tools to start solving it.